Hi everybody. Today we are going to be learning section 10.3, which is going to be on polar coordinates. Okay, so what are polar coordinates? It is a different coordinate system than what we are used to, which is Cartesian coordinates. Okay, the idea is that if you take any point, instead of writing down its x and y coordinates, what we could do is instead figure out how far away that point is from the origin, and we call that number r, and also figure out what angle it makes with the positive x-axis, and we call that theta, and then that actually gives us a unique point, p, which we call r theta. Or in other words, r theta would be the coordinates of that point in polar coordinates. Okay. Now, this is unique, right? As long as I tell you an angle, think of the theta as being the direction you walk in, and then r is how far do you walk in that direction, right? And so this will give you a unique point. Now, just because a coordinate will give you a unique point, it does not mean that a point has a single coordinate, right? So we also can use negative r as well. Okay, so as an example, if instead we were to write down negative r and then take theta and add pi to it, this would actually put us in the exact same spot. Why is that? Because theta plus pi tells us to walk in this direction, right? But then negative r is saying to walk backwards, and so you would end up at the exact same point. Okay, so we have to be careful because in polar coordinates there is more than one way to name a point. Okay, however, each name does only put you at one point. So let's practice using polar coordinates. So I want us to plot the points whose polar coordinates are given. So first, how about the point A? So I'm going to write down some points here and we're going to plot them, okay? So first one is going to be 1, 7 pi over 4. The next will be point B, which is 2, 3 pi. The next will be point C, which is 1, negative 2 pi over 3. And the next one will be D, which is negative 3, 3 pi over 4. And then finally, the last one, which will be 0, 11 pi over 27. Kind of a complicated angle for that one, but you're going to see that it won't end up mattering, okay? Okay, so let's draw our coordinate system. Now, the way that you plot a point in polar coordinates is you look at these first coordinates here, right? Remember, everything that we see above on the left here, these are the r's, and everything we see on the right are the thetas. So because r's, the biggest r that we ever see in magnitude is a 3, and so what that means is we're going to have circles here. So I want you to imagine that these are circles of radius 1, of radius 2, and of radius 3. Okay, so this is 1, 2, and 3. Okay, and so let's work on each point here. First, let's look at point A. It says that we want the radius to be 1. In other words, it sits on that circle. and the angle is 7 pi over 4. So 7 pi over 4 is, of course, this angle. And we know we're going to sit on the circle of radius 1. And so this guy right here would be A. Okay? All right, let's look at point B. It says we go 3 pi and then 2. So 3 pi is the same as the angle pi, right? So we know we're just moving straight to the left. And we go 2 spaces, and so that would be right here. This would be B. Next, sitting on a circle of radius 1, except we're going backwards 2 pi over 3. Backwards 2 pi over 3. So where would backwards 2 pi over 3 set us? Well, it would be, think of it as negative 120 degrees, right? And so it's 60 degrees below the pi mark, and it's on a radius of 1, so this would be something like right here. Okay, so this point right here is C. Next, let's look at D. We go 3 pi over 4. So I want to illustrate this here. 3 pi over 4 is this angle, except we're moving negative 3. This means we move backwards 3 spaces, and so it actually puts us right here. This is point D. Finally, notice that R is 0. What do we get when R is 0? Well, since we're moving 0 steps away from the origin, it doesn't really matter what the angle is, okay? So we are still at the origin. Okay, so this would be E. Okay? So this is just an example of how you graph points, or how you plot points in polar coordinates. Okay, so fact, representations, I mean, as you've probably noticed by that last example, representations are not unique in polar coordinates. Okay, so the point r theta, if we add any multiple of 2 pi to theta, we know that we're going to get the same point. So we can actually call this theta plus 2 pi n. And we know that for n being any integer, so n is any integer, we know that that's going to give us the exact same point. But that's not all. We also know that if you shift to negative r instead, then all you have to do is add pi to the angle we had before, and then we would end up with the same. So I'll write it like this: theta plus pi, that's a pi shift, but then plus 2 pi n yet again, right? Because we know that any 2 pi doesn't change anything. Okay, so there are, in other words, there are an infinite number of ways of naming every point. Okay? All right, so this is important to know. So let's go to the next part, which is how do we convert? So let me write conversions from one coordinate system to another. So first, let's talk about how we go from polar to Cartesian. Okay, polar to Cartesian. Polar means we're given an r and a theta, and then we need to figure out the x and the y coordinate. So many times we need to be able to switch between the two coordinate systems, okay? So I want you guys to think about this, okay? If we have this point r comma theta here, that means this is r and this is theta. But the idea is that if we were to create a right triangle, then this would be our x coordinate and this would be our y coordinate. So how do we find x and how do we find y? Well, it's true that sine of theta is equal to y over r, and cosine of theta is equal to x over r. So what does this mean? This means that x is equal to r cos theta and y is equal to r sine theta. And so that is how we would find our new point. Okay, so this is our Cartesian, this is how we convert from polar coordinates to Cartesian coordinates. Okay, now how would we go from Cartesian to polar? Remember, Cartesian means that you're starting with an xy, right? Okay, so let's draw a picture of this, right? We're starting with the point. This is x and this is y, and then we want to figure out what that theta is. We need to find a relationship, okay? We also need to figure out the r here. So how would we find r if we know those two? Well, we know by the Pythagorean theorem that x squared plus y squared is equal to r squared. So if we know x and y, we should be able to find r. But what would r then be? Well, r is equal to the square root of x squared plus y squared. Now, of course, this will give you the positive r. If you want the negative r, then just make it negative, okay? But usually, the positive r just makes things more straightforward if we stick with that. Now, what about theta? Well, we know that tan theta is equal to y over x, right? So what does this mean? Well, this means that tan theta is y over x, which means that theta is the arctan of y over x. Okay? However, there is something to know about arctan of y over x, okay? Theta is going to equal the arctan of y over x. However, arctan only gives you angles that are in quadrant 1 or quadrant 4. So if your point is in quadrant 1 or quadrant 4, then you just use arctan. Okay? However, if your point is in quadrant 2 or quadrant 3, then arctan will actually be off by pi. And so you're going to use theta is arctan of y over x plus pi if you are in quadrant 2 or quadrant 3. Okay, none of the arc trig functions or the inverse trig functions put you in the correct of 4 quadrants, right? You had to restrict the domain to begin with to define these functions, and so you need to make this adjustment yourself. Either you add pi to it or not, depending on what quadrant the point is in. Okay, so this is how we convert from one to the other. So let's do a tiny bit of practice here. We'll do a quick example before we move on to the next thing. Okay, so this will be example 2. I want us to convert 1 to pi over 3 from polar to Cartesian. Okay, so remember guys, this is r and this is theta. So all we need to do is use the formula, right? X is equal to r cosine theta, which is the same as 1 times cosine of 2 pi over 3. Cosine of 2 pi over 3 is a half, so this would just be the point, negative a half, right? So this would just be the point negative 1/2 for the x coordinate. And for the y coordinate, that's equal to r sine of theta, which is equal to 1 times sine of 2 pi over 3. And if you take the sine of that, that gives you a positive root 3 over 2. Okay, so our Cartesian point is negative 1/2, and then root 3 over 2. Okay, so that's it for that problem. So hopefully you can see it's really straightforward to go this way. Let's convert the other direction. So let's convert, for example, the point -3, -4 to polar coordinates. Okay, this means that that's our x and that's our y. By the way, remember to always check what quadrant something is in, okay? So -3, -4, this is, think about this. -3, -4 is somewhere over there. In other words, this is quadrant 3, right? This is a quadrant 3 point. So we know we're going to need to make that adjustment with the arctan, okay? Let's start with r, though. We know that r is equal to the square root of x squared plus y squared, which is equal to the square root of 9 plus 16. In this case, it ends up working out nicely. But if it works out to be a square root that you can't simplify, that's totally fine. You would just leave the square root in your answer, okay? All right, so that is the r. How about theta? We know that theta is going to be arctan of y over x. So -4 over -3 is the same as 4/3, but I have to add pi to it. Now, arctan of 4/3 is not a nice angle. It's not one of the special angles that we know. So I'm just going to leave it like that. Okay, so then our polar point would be 5, arctan of 4/3 plus pi. Most of the time it'll be a nice angle, but sometimes it's not, and we have to be okay with that. Okay? So now that we understand the basics of the points, let's go a little bit further and talk about polar curves. Okay? So an equation f of r theta is equal to 0. We call this a polar equation. Polar equation. A graph when you graph those points on a coordinate axis, a graph of f of r theta equals 0 gives you a curve called a polar curve. Okay. as expected, a graph, the word graph just means that it contains all the points. I'll just say all polar points that satisfy the equation. Okay, so just like you're used to graphing of equations in the past, right? If a point satisfies the equation, then it goes on your curve. Okay? So let's talk about the natural equations first in Cartesian and versus polar, okay? So first of all, in Cartesian coordinates, we have what we call the natural equations. What is the easiest equation that you can build in a coordinate system? Well, the easiest ones that you can build are just when you let x equal a constant or y equal a constant. So we know that when you let x equal a constant, you get a vertical line, right? And when you let y equal a constant, you get a horizontal line. So these are the natural equations, and so what this means is that Cartesian coordinates are good when you have vertical or horizontal lines because they lead to simple equations, right? What is a Cartesian rectangle? We all know what a rectangle looks like, and so a Cartesian rectangle is exactly what you would consider to be a normal rectangle. So if you let x range from A to B, and you let y range from C to D, then what do you end up with? You end up with something that looks like this, right? So if this is A and this is B and this is C and this is D, then this is what we end up with, right? We end up with this rectangle. Okay, you could see all of the little pieces in this, right? This bottom line is y equals C and the top line is y equals D. And the vertical line on the left is x equals A, and the one on the right is x equals B. Okay? So this is what a Cartesian rectangle is. Many times we just call this a rectangle, right? In English, we never usually call this a Cartesian rectangle. The reason I want to make this distinction is now we're going to find out what happens in polar coordinates. What are the natural equations there? Okay, so let's focus on polar now. And so let's talk about the natural equations in polar coordinates first. So let's start with r is equal to a positive constant. Okay, r is equal to a positive constant. What happens if you fix r, but you let theta be whatever you want? Well, if you fix r, remember r is how far away you are from the origin. So if you fix that and you go all the way around, what do you get? You get a circle. So you get a circle whose radius is k. A circle whose radius is k. Sorry, that's a really horrible looking circle. Let me try to draw a better picture here. There we go. You guys deserve better than that. Okay, so that's a circle with radius k. Well, let's write this down. Circle, I'll write this down underneath. So this is a circle with radius k centered at the origin. Okay, so this is a natural equation. This popped out naturally. Now, what about if you fix theta equal to k? So with theta equals k, let's think about what that means. That means the direction is fixed. However, the radius could be anything. So what do we get? Well, again, let's say you fix theta and theta is like this. What this means is you get that entire ray. So I'm going to put it this way. Okay? So what you actually get is a ray with initial point, the origin with angle k. And remember, the angle is, of course, in radians, right? It's always in radians when you're talking about polar coordinates. So let's put rays and circles together. Just like rectangles in Cartesian coordinates are made out of taking these two pieces and building, letting x range from one to the other, letting y range from one to the other. We're going to do the same thing now with these two shapes, okay? So what does a polar rectangle look like? Well, let's suppose that r goes from A to B, and theta goes from alpha to beta. Okay. What does that look like? So this is what you would get, okay? You get this like circular chunk here. So this is pointing to theta equals beta, and this right here is theta equals alpha, and then this right here would be r equals A, and then this guy would be r equals B, and this would make our rectangle. Right? It doesn't really look like a rectangle, but that is what we call a polar rectangle. Now, of course, there are special cases of this, okay? This is the general one, but what happens if r is between 0 and A, and theta is between alpha and beta? Well, if r is between 0 and A, that means that you would actually touch the origin, right? So this is what you would get. You would get like a sector of a circle. This is r equals A, and then this guy right here is theta equals beta, and then this guy right here is theta equals alpha. Okay, so this is considered to be a polar rectangle also, right? What about if you were to make r go from A to B, but theta goes all the way around from 0 to 2 pi? Well, what's going to happen is you actually now have two circles, right? So if this is A, so if this is r equals A is the inner circle and r equals B is the outer circle, but theta goes from 0 to 2 pi, what you actually get is this entire shape. This is considered a polar rectangle also. Okay. So we're not done. There is one more case that might happen, is what happens if theta goes from 0 to 2 pi, but r also goes from 0 to B? Well, that's just an entire circle, right? This circle on the outside is r equals B. So this gives you everything. So these are an example of the fact that rectangles can look very different in polar coordinates, right? Now, what we want to practice, though, is being able to sketch general polar curves. So let's shift our discussion now to polar curves. Remember, polar curves polar curve sketching, remember, this is when you have f of r theta equals 0, but what we want to do is we want to usually have it in terms of theta, right? We want to have r isolated, r equals f of theta. So, if you can't solve for r, then you would get the one on the left, but if you can solve for r, then you would get the one on the right. So what are the steps for sketching? So, step 1, okay. So here is what my suggestion is, okay? So if you're doing r equals f of theta, what I like to do is I like to use information about the Cartesian graph y equals f of x and use that to help us visualize what's going on with the polar sketch. So since f is a function of theta, what we do is we can sketch y equals f of x and use it to get several points. X, y, which remember, those really translate to r theta, right? Y. Let me fix this, okay? Because you're replacing theta with x, I apologize. So this will correspond to theta r. This will correspond to theta r, right? Because what we're doing is we're replacing r equals f of theta with y equals f of x. So essentially what we're doing is we're replacing all the thetas with x's and all the r's with y's, and we use it to get a lot of points. But those are really polar points. And then step 2 is going to be to connect the dots. To form a polar curve. Now, as a note, you might get lucky and be able to bypass the above. So when possible, or let me actually write it this way. Sometimes it is possible to convert your polar equation into a known Cartesian equation. What this using the fact that r squared is equal to x squared plus y squared, and a lot of times we use the fact that r cos theta is equal to x and r sine theta is equal to y. Okay, so sometimes it is possible to convert, so this works best. But I should point out it doesn't always work. So let me just say this works best when it works. Okay, so the method above always works, but the note sometimes works, and if we can do it that way, we will do it that way. Okay? Okay, so let's practice sketching some polar curves, okay? So let me do our next example. I believe we're on example 4, right? So sketch the polar curve. You know what? I'm going to make this a single problem. Sketch the polar curve r equals 2 cos theta. How would we sketch this? So we are actually going to try converting this into a Cartesian equation, okay? So how do we convert it? Well, isn't it true that if I multiply both sides by r, I have r squared is equal to 2r cos theta? Right? But this guy is really x squared plus y squared, and this guy is x, and so what we end up with is x squared plus y squared is equal to 2x. What kind of equation is this? Well, it would help if we know what this looks like. For those of you that remember your pre-calculus or your algebra, right? Isn't this really, can't I write it this way? And so if I complete the square here, if I add 1 to this and then add 1 to that, what I actually end up with is x minus 1 squared plus y squared is equal to 1. So this is actually a circle. The radius is 1, and the center of the circle is 1, 0. What does this mean? So this is 1, 0, and so this is what our polar curve looks like. Why is it not centered at the origin? This is not a natural unit circle, right? The natural unit circle at the origin would be the equation r equals 1, right? That would be the unit circle. But the fact that we have r equals 2 cos theta, that's how you shift circles in polar coordinates, right? Okay, so if we want to be, even more specific, that's the point 1, 1. This is the point 2, 0. This is the point 1, negative 1, and this is the point 0, 0. Okay. All right, so our Cartesian equation for the curve is right here. This is the Cartesian. Okay, now that one was a bit easy, right? We're going to be getting much tougher now, okay? So number 5. I want us to sketch the polar curve r equals 1 minus sine theta. Okay, so what we're going to do is we're going to rewrite this using Cartesian coordinates, but we are not doing a conversion here. Okay, we're not. This is not a conversion. What we're doing is we're just going to use the sketch that we're about to do in order to quickly determine the points and the patterns that we're looking for, okay? So what does 1 minus sine of x look like? Well, we know this is periodic, so I just want to sketch one period here, right? So this is basically the graph of negative sine x, but shifted up one space. So what does that look like? That means instead of starting at the origin, it starts at 1, right? So it starts right here, this point right here. And then minus sine x, so that means that it goes down instead of up. So it's going to look something like this, and then like that. Let me make this part on the left a little bit better. I don't like the way that this came out. So it's going to look something like that. Okay? So this is 1, goes to a height of 2. Okay. This is pi right here. This is pi over 2. And this is 3 pi over 2. Now, this is not a sketch of the polar curve, right? This is basically we have cheated and we've done a Cartesian graph, right? This is not a polar sketch. But what we're going to do is we're going to translate points on here to, so this is, what we're doing is this is theta and this is r, right? So what we've done is we've essentially just sketched this in using Cartesian, pretending like they're x's and y's, just to see what's happening with these points, but then we need to translate it, okay? Now look, the largest r that we ever get is an r of 2, right? Sorry, I know that's not straight, but that's okay, okay? So that means that when we do this sketch here, we know that we are going to need these circles already sketched, okay? So there's my circle of radius 1. There's my circle of radius 2. I'm going to use red to do the sketch itself, okay? So look, every point that I put here is going to be a point over here. So let's start with this point right here. Okay, what point is that? That's theta is 0 and r is 1. So what does that correspond to down here? Theta 0, r is 1 corresponds to right here. Okay? Next, we're going to here. Theta is pi over 2, r is 0. Well, when r is 0, we know that's the origin, right? So that's going to be right here. How do we connect, though? Well, it's going to help to know a middle point right here, right? When theta is pi over 4, r is 1 over root 2. So what does that mean? Pi over 4, 1 over root 2, it means we're about right there on the circle. Okay? So we already know then that the circle is going to do something like this. Okay? Now what? Well, now we have the point right here, which is the point of pi 1. When theta is pi, r is 1. So pi 1, remember pi is aiming to the left, and 1, so that would be right here. What would be in between here? Well, that would be 3 pi over 4, and it's a positive number, so it's somewhere like right here. And so we know it's going to be something like this, okay? Sorry, that last one doesn't connect. Let me connect it. Okay, so this is what we have. Let's keep going here. What would this point up top be? This is 3 pi over 2 is theta, and r is 2, so we're way down here, aren't we? And what would the in-between be? We know that's going to be a positive, so it looks something like that. And then that last point, 2 pi 1, that's going to be where we started, and so it looks something like this. Okay, so there you go. I mean, if you are confused by this, you can find a lot more points here. And you can even make a table, right? If you were to make a table of theta and r from this, right? So the first dot that we had was theta was 0 and r was 1. And then we had pi over 4 and then 1 over root 2. And the whole point is you can do enough dots using that sketch up there to sketch the polar curve accurately. You'll notice also that this looks like a heart. This sketch actually has a name. It's called a cardioid. So this is just one example of some of the interesting types of sketches that we can get using polar coordinates. I'd like to do another one here. So let's sketch the polar curve r is equal to cosine of 2 theta. This should be an interesting one. Okay. All right, so again, we are going to just write this as y equals cosine of 2x. And what does y equals cosine of 2x look like? Well, we know that this is just a graph of cosine, except we actually need 2 periods in order to make it to 2 pi. Right? That's because the period is just pi for this cosine curve. Okay? So this would be pi, right? That's halfway. And then this would be 3 pi over 2. And then this guy would be pi over 2. Okay? And then we've got these in-between points, which I should label because they're going to come in handy here. That guy right there would be pi over 4. This guy would be 3 pi over 4. This guy would be 5 pi over 4. And this guy would be 7 pi over 4. So again, the reason we're doing this is because we have a lot of information now that we can deduce regarding the actual polar curve. Now, I want you to look for a second, right? This is 1 and this is -1, which means everything takes place within the confines of the unit circle, doesn't it? Okay, so this is what I'm going to do. I'm going to make the unit circle very big here. Sorry, that last part didn't look great. Let me make this a little better. Okay, that's a bit better, okay? So there's our unit circle, and we want to translate what we saw. Let's start with this point over here. Okay, so that would be the point where the angle is 0 and the r value is 1. So that's right here. Okay. Next, at pi over 4, at the angle of pi over 4, so I'm going to draw an angle of pi over 4 here. At an angle of pi over 4, we reach the origin. Now, I know it's just the origin, but the idea is that we can't cross that dotted line. So it looks something like that. Okay? So next, let's go with this point. Now, be very careful because this point down here, the r is actually -1, so we're going in the opposite direction. So even though it says an angle of pi over 2, it's going to actually put us down here. So we know that it looks like that. Next, we're going to go back to the origin, but at an angle of 3 pi over 4. 3 pi over 4, I'm going to have to cross it over here, okay? Now, the reason I'm going to the negative side is, again, because all the r's are negative underneath there, right? And so I know I'm actually going to be behind this thing. It's going to look something like that. Okay? Next, we want to get to this point. This is the point where the angle's pi, and then we're at 1. Okay, pi 1, that's right over here. So we know it goes like that. And we're halfway done with the picture. If we continue on with this logic, what's going to happen is that this is going to go like this, and then we're going to go like this, and then finally the last piece is going to be like that. Oh no, sorry, we got one more piece, and then it goes like that. So it's really cool. We actually get sort of this we get what we call a four-leafed rose. Okay, four-leafed rose. Every single problem is unique. I highly recommend practicing these because you need to figure out how to take a Cartesian sketch like this, but then figure out how to take those points and translate them to polar points, right? And that's all we're doing here. Every single curve is different, but polar curves do lead to some really interesting things. Okay, so this is a big section, right? Because what we're actually going to do now is we're going to talk a little bit about some calculus, right? We haven't talked about derivatives or tangents or anything like that. So let's talk about tangents to polar curves. So in particular, remember, I want you to recall from parametric equations or parametric sections that dy dx is equal to dy dt divided by dx dt. But what's our parameter now? Okay, well right now, theta is our parameter, so this means that dy dx is equal to dy d theta divided by dx d theta. But what are x and y as functions of theta? Well, I want you to suppose that we know that r is equal to f of theta, right? Suppose that this is our polar curve. Okay, we actually have conversion formulas, right? If x is equal to r cosine theta and r is equal to f of theta, doesn't that mean that x is equal to f of theta times cosine theta? And if y is equal to r sine theta, doesn't that mean that y is equal to f of theta sine theta? So this means that the same formula is still going to work, except we need to take the derivative of each of these with respect to theta. Okay, so what would dx d theta equal? Well, that means we're taking the derivative of this guy with respect to theta. So what would that be? Well, we need to use the product rule to do that, right? So we end up with the derivative of the first, f prime of theta, times the second, plus the first times the derivative of the second, so that's negative sine theta. And so I'm actually going to start writing what this fraction is. What we just found here is the denominator, right? Because that's dx d theta. So how do I write that? Well, f prime of theta, remember, that's f of theta is really r, so there's a nice way to write that. Wouldn't this just be dr d theta? So dr So f of theta is really r, so I'm going to call that r sine theta. Now, what would dy d theta be? Again, we are differentiating this guy now. This means we're going to do the derivative of the first times the second plus the first times the derivative of the second. And so if I were to write that with our notation, I get the following. dr d theta I remember sine theta plus, and then r cosine theta. Okay, so this would be our formula for dy dx. Now, I would not memorize this if I were you. I think it's just, there's too many formulas to memorize. So really all you need to remember is this relationship, right? X is r cos theta and y is r sine theta. You've got your polar curve. And then just use the product rule, okay? You do not need to memorize that formula. So we can remember the formula or just use the given relationships. I opt for using the given relationships, right? You should know this part anyway from the parametric section. So really it's just a combination of that with our new polar equation formulas, right? So let's do a quick example here. This will be number 7, I believe, right? Grade number 7. Let's do this example with the cardioid, right? We had a nice problem with the cardioid. So for the cardioid, r equals 1 minus sine theta, find the slope and tangent line when theta is equal to pi over 4. This will be part A, and for part B, I want us to find the points on the cardioid where the tangent line is horizontal and vertical. Okay, so let's go ahead and practice taking our derivative, okay? So remember, x is equal, this is how I would do it, okay? X is equal to r cos theta. This is just something we know that's always true about polar coordinates, but we have r equals 1 minus sine theta, so just replace it. So this means that x is equal to 1 minus sine theta times cos theta. Okay? So we can go ahead and take the derivative right away. What would dx d theta be? Remember, it's the derivative of the first. I'm going to use the product rule. The derivative of the first, that's negative cos theta times the second. So that's negative cos squared theta, right? Plus the first times the derivative of the second. So that's what we have for dx d theta. And let me go ahead and simplify this, okay? If we simplify this, we get negative cosine squared theta, and then we have minus sine theta, and then we have plus sine squared theta. Now what I want to do is I want to rewrite this using only sines. So because I have a cosine squared theta, I know cosine squared theta is 1 minus sine squared, so that means this is sine squared theta minus 1. And so here's what we end up with. 2 sine squared theta minus sine theta minus 1. So I'm going to leave it like that. So that's dx d theta. What about dy d theta? Well, let's write down what y is. Y is equal to r times sine theta. That's 1 minus sine theta times sine theta. So I'm ready to take my derivative. Let me actually do that on the next line here. Dy d theta is equal to, it's going to be the derivative of the first times the second plus the first times the derivative of the second. What is this equal to? So it's negative sine theta cos theta plus cos theta minus sine theta cos theta again. And so if I combine my like terms here, what I get for dy d theta is negative 2 sine theta cos theta plus cosine theta. Okay, look, this is dx d theta, and this is dy d theta. So now we can find their derivative by just dividing them, okay? So this implies that dy dx, remember, we know that this is dy d theta divided by dx d theta. So what is this equal to? Well, dy d theta is that guy on the bottom, so it's, let me write it in the positive order first. Cos theta minus 2 sine theta cos theta. And dx d theta is 2 sine squared theta minus sine theta minus 1. Now, this is nice. We found our derivative, and so part 1, or part A, asked us to find the slope in the tangent line when theta is equal to pi over 4. So let's start with the slope. The slope is going to be dy dx at theta equals pi over 4. So let's go ahead and plug in pi over 4 into this. Okay, we've got 1 over root 2 minus 2 times 1 over root 2 times 1 over root 2, because cosine of that is the same thing, over 2 times sine squared theta. Again, that's 1 over root 2 squared is a half, minus 1 over root 2 minus 1. What do we get here? Well, root 2 times root 2 is 2, so that cancels with those two. That cancels with that. And if we multiply top and bottom by root 2, we actually end up with the following. 1 minus root 2 divided by, what do we get here? We actually have a 1 minus 1 here, so actually this guy and this guy cancel each other out. So we're left with that, which is actually root 2 minus 1. Okay, so this is what I get for the derivative. So root 2 minus 1, this is our slope when theta is pi over 4. Okay, now what about the actual tangent line? Well, we need to know what the point is at theta equals pi over 4. Okay, so remember, our point, x is equal to r cos theta, right? So x is equal to r times cosine of theta. So if we plug in theta equals pi over 4, what do we get for our x coordinate? We end up with 1 minus 1 over root 2 times 1 over root 2. So x is going to be 1 over root 2 minus a half. Okay. And Let's combine this into one fraction. Why not? So this is really root 2 minus 1 over 2, right? I just multiplied top and bottom of this guy by root 2, right? Okay, so this is our x coordinate, and then our, look, we can call this x naught, right? This is our point on the line. What about y naught? Remember, this is going to be our sine theta. So it's 1 minus sine theta times sine theta, and this is at theta equals pi over 4. But because pi over 4, sine of that is the same as cosine of that, we're going to get the exact same point. So we know this is going to be root 2 minus 1 over 2. Remember, guys, tangent line, or any line really, the equation of a line is always y minus y naught is equal to the slope times x minus x naught. And so if we want to write this as an equation, we end up with y minus this is equal to the slope times x minus this. This would be our tangent line when theta is equal to pi over 4. If we were to try to visualize this in our cardioid picture, let's go back to it, right? Our cardioid was right here, and so what we're saying is that at pi over 4, we're probably about right here. So this is our tangent line that we're talking about. You'll notice that this does have a positive slope, right? This has a positive slope. And if you come back here to our problem, our slope was root 2 minus 1, which is positive, right? And so what we wrote down does make sense. Okay, the next part of this question was to find the points on the cardioid where the tangent line is horizontal or vertical, right? Okay, so how do we do that? We need to set this guy equal to 0. So we're going to take this equation and manipulate it a little bit, okay? We're going to factor the top and we're going to factor the bottom on the next line. Okay? So dy dx, right? What would dy dx equal? I'm going to factor the top. So on the top, I can pull out a cosine, and then I have 1 minus 2 sine theta. So I have this. And for the denominator, I can actually factor it like this. Think about it this way, right? If it was a 2x squared minus x minus 1, doesn't that equal, let's see, 2x1, x1. So this is plus minus, right? And so in other words, this would be 2 sine theta plus 1, and then sine theta minus 1. 2 sine theta plus 1, sine theta minus 1. We need to get these things to equal 0, right? Because that's how you find horizontal and vertical tangent lines. So where are we going to get a horizontal tangent line? Horizontal tangent lines are going to occur where we get a slope of 0, right? And so this is going to be, let's figure out where the top is 0. So cosine of theta is 0. This means that theta is equal to pi over 2 plus any multiple of pi. And what about where 1 minus 2 sine theta is 0? This means that sine theta is a half, which means that theta is going to equal, so which values of sine have a value of a half? So which thetas have a sine of a half? That would be pi over 6 and 5 pi over 6, right? You know what? Maybe I should just realize that we are using only from, theta lives from 0 to 2 pi in this picture, right? Because that gives you the whole cardioid. So let me actually split these up. Instead of putting plus pi n here, the only two options are going to be pi over 2 and 3 pi over 2, right? So all of these seem to give us 0 for the numerator. However, we need to be careful because the denominator should not be 0. So we also want 2 sine theta plus 1 to not be 0, which means we want sine theta to not be negative a half, which means that we want theta to not equal, where is it negative a half? 7 pi over 6 and 11 pi over 6. So we're okay there, right? None of our values we got above was equal or were equal to that. So we also want sine theta minus 1 to not be 0, which means we want sine theta to not be 1. Where do we have a sine equal to 1? That means that we want theta to not equal pi over 2, right? Sine of pi over 2, that's the only time that we get a sine of 1, which means we need to throw this value out. Okay, so where are the points where we get a horizontal tangent line? We get it where theta is equal to, let's write these all down. We got pi over 6, 5 pi over 6, and 3 pi over 2. These are all the horizontal tangent line values. I shouldn't say at equals. I have a little mistake here. This should say at theta equals all these things. Okay. Now, where would those be? If we come back here, this should be clear, right? Theta's pi over 6 is going to give us this guy. I know my picture is not great, but that should be an angle of pi over 6. And that should be the angle of 5 pi over 6. And you'll notice that the 3 pi over 2 tangent line gives us this bottom horizontal one. So those are the only 3 horizontal tangent lines, right? We've got one right here, we've got one right here, and we've got one right here. Okay? Now let's do the vertical ones, okay? Let's do the vertical ones. Where do we suspect? By looking at the picture, we suspect that there are actually going to be 3 of them, right? We know that that's one. We know that we have one on the other side. And also it seems like there might be one right up here. So we expect 3 of them. So if we look at what we have here, if we want to do vertical tangent line now, we need to be careful, right? We want values where the bottom is 0 and the top is not, okay? So what do we have? We know that at 7 pi over 6 and 11 pi over 6, we know we're going to have a vertical tangent line at theta equals 7 pi over 6 and 11 pi over 6. How do I know that? Because these are values that are 0 on the denominator, right? Everything that we see here is the denominator, and everything that we see over here is the numerator, right? So if we're looking at values where the denominator is 0 and the numerator is not, we know that 7 pi over 6 and 11 pi over 6 are 2 of them. Now, what about pi over 2? The problem with pi over 2 is we actually get a 0 on top and bottom. So we're going to need to do a limit, okay? Because we have 0 over 0 here, right? So what we want to do is we want to do the limit as theta goes to pi over 2. It doesn't matter from what direction, so I'll just put from the left. And we want this to be for the derivative here. We have cosine of theta, 1 minus 2 sine theta. Over, and then the bottom, remember, is 2 sine theta plus 1 times sine theta minus 1. Now, yes, this is equal to 0 over 0, so we can use L'Hopital's rule on this, right? However, it's worth paying attention to which terms are giving us 0 because we can actually simplify our calculations here. So you notice that these are the two terms that are giving us the 0 over 0, which means the others are not, and we can actually do that limit separately, right? We can actually do this. So here's the stuff we can calculate. Now this is a lot easier to do L'Hopital's rule on. Notice that the guy on the left, we do not need L'Hopital's rule, right? Because if you were to plug in pi over 2 here, sine of pi over 2 is 1, but you get 1 minus 2, so this is just equal to negative 1 over, let's see, sine of pi over 2 on the bottom is 1, times 2 is 2, 2 plus 1 is 3. So the first guy gives us negative 1/3. So really, this is the guy that gives you 0 over 0 that we can use L'Hopital's rule on, right? So what is this going to equal with L'Hopital's rule? The derivative of the top is negative sine theta, and the derivative of the bottom is cosine theta, right? So what does this give you? Well, if you plug in pi over 2 from the left, we recognize this is tangent. We know this shoots up to infinity. Or another way you can think of this is this guy goes to, so this limit itself, you can think of it as going to negative 1 over 0. So the whole limit goes to some value. We don't care whether it's plus or minus infinity. It doesn't actually matter, okay? The point is it gets infinite. And infinite multiplied by this negative 1/3 does not change the infinite value, okay? What does this mean? All that work was to make sure that we had a vertical tangent line there, and we did, okay? So this means that we actually have 3 vertical tangent lines, one at pi over 2, and then the other 2 at 7 pi over 6 and 11 pi over 6. So if we come back to our picture, it's the exact 3 that I drew here, right? This would be 7 pi over 6. This would be 11 pi over 6. And then this guy right here, this guy is right at pi over 2. Okay? Now, one thing I should point out is I didn't actually find the points where those happen. What I did was I found the theta values, right? So find the theta values. You can easily convert those to points, but I think you guys get the idea of how you answer a question like this. Okay, guys, I know that was a long video. Thank you so much for sticking with it, and I hope it was helpful.